So we enter a new number system called the complex numbered system. And as we've talked about a little bit before, or I showed you in a video, complex number system came about when mathematicians were trying to solve a problem similar to this, where we had some squared term plus another term was equal to 0. We end up trying to find a square root of -1 in the end. And knowing that we want to take and find a number that multiplies by itself and gets you -1 is a pretty hard thing to do. So like any mathematician, when they had problems back in ancient history of finding an answer and they didn't have enough numbers to use to find that answer, they created a new number system. And that's exactly what they did here. So they started this number system by saying, well, hey, if we ever get a square root of -1, we're going to call that I. And that's by definition. You can't question us because we're really smart guys, and that's just how it's going to be. And we're also going to say that the square of I is going to be -1. That's also by definition, no challenging. And by the way, let's just set up a whole new number system called the complex number system, where a number can be written in the form of a plus bi, where a is the real part of that number, and bi, or the I part of that, is the imaginary part of that number. The whole thing is a complex number once again. Now, if you note, if I have I squared is equal to -1, that means the square root of a times the square root of b can equal the square root of ab, because if I have -1 and a -1, that would equal 1. And that's just not happening here by this definition. So like they said, accept it, deal with it, and move on. All right? So this property is not going to work in our complex number system. So we're going to start out by simplifying this concept of I to the 73rd power. All right, well, the way I look at it is, if I know that I squared is equal to -1, then I to the I squared, which is I to the 4th, is equal to 1. So what I try to do is I try to figure out, well, first of all, how many I squareds are in here. A lot of people like using the I to the 4th because they like positive values, but I like, I squared terms. So if I go I squared, and I want to know how many I squareds are in 73, well, I know 2 divides into 72 36 times. So I can then say that this is 36, and I'd have an I left. Now I know I squared is -1. That's the 36th power. And we have I. I can do -1 to the 36. That's just 1 I, or I. Simplifies out. So what I would do is I would break this down into how many I squareds you have, and then figure out what you have left. Now, if we want to simplify a complex number, well, we've simplified things like the square root of 50 before. That's not a big deal. And this isn't going to be a big deal either, because what we're going to do is anytime we see a square root of a negative, we're going to call that a complex number. So we're going to make this an I, and then tack on the coefficient of I to that. And the square root of 50 is going to be that B coefficient, if you will, back in the other slide. And we know how to simplify that. That's 5 root 2, right? And therefore, we write this complex number, which is really just the imaginary part, because the real part doesn't exist in this case. We don't have one, is 5I root 2. Same idea here. We just talked about how the square root of a times the square root of b isn't equal to the square root of ab. So what we're going to do is we're going to make each of these a complex number by throwing that I out there. And then we can say, well, hey, I've got two i's sitting right there and I'm multiplying, so that's I squared. And this is the square root of 200. I squared we know is negative 1. Square root of 200 breaks down into 10 root 2. So this is negative 10 root 2. Here is also a complex number, but we have an I in the denominator, and we know I is really the square root of negative 1. So we're not going to be allowed to have that square root in the denominator, so we have to rationalize by a number that gets this off the bottom. And if I just rationalize by I over I in this case, that gives me a form of 1. So the value of this expression is not going to change. That's 4i over 5i squared. But we know I squared is negative 1. So this is 4i over 5. And like we said, there's a negative 1 on the I squared, so I'm just going to pull that guy out. We can distribute these just like we would any normal set of binomials. And we have the 40. We have 20i and another 20i. And we've got 10i squared. Real parts with real parts, imaginary parts with imaginary parts. I'm going to rewrite this because I squared is negative 1. So that's negative 10. This is 40i. This is still 40. So this is 30 plus 40i. Again, this is my real. This is my imaginary. Here we go again with a root in the negative, if you will, even though it's an I, again, square root of negative 1. Because I have a binomial, I need to rationalize by the conjugate. So that's 2 minus I, 2 minus I. Distribute away, negative 10 plus 5i over 4 minus 2i plus 2i goes, minus I squared. So in this case, I've got negative 10 plus 5i over 4 plus, this is negative 1, and a negative is a positive 1. And then I have negative 10 plus 5i over 5. Now, we can factor that, or we can split it up into two parts. A lot of books will actually give answers in this form. All right, where this is a negative 2, this is plus I, so it comes out nice, but in several cases, if there's a fraction here and a fraction here, they'll leave it in the real part and the imaginary part. You could have also, in this case, factored out a, I don't know, let's factor out a 5, and then you get your negative 2 plus I over 5. Those reduce because they're both real parts, and we get an answer of negative 2 plus I. Same concept, different way of going about it. And real similar problem to the last one, except now we're going to take and subtract the results of the rationalizations. So this is 6 minus I, 6 minus I, 4 minus 2i, 4 minus 2i. Go ahead and do all your multiplications. So you got 24 minus 4i over 36 minus I squared. It's going to be subtracted by 12 minus 6i over 16 minus 4i squared. Clean all those up a little bit. This is 24 minus 4i over 37. And this is 12 minus 6i over 17. I'm going to need a common denominator, which is just going to be the product of those two. So 37 times 17 is going to be 629. Write that down twice. means this is going to get a multiplication of 17 over 17. This is going to get a multiplication of 37 over 37. All right. So in doing that, I'll just multiply 17 times 24, get me my 408. 17 times a negative 4 gets me, what, 68? It's a terrible 8. And then 37 times 12 is going to get me about 444. Whoops. All right, and 37 times 6 is 222. And then I'm just going to subtract, in this case, we'll go 408 minus 44, or 444, sorry. I'm going to get negative 36. And then 68 minus, or actually it's going to be 68 plus 222, which is going to give me 154. All over 629. All right, and those are the basics of manipulating complex numbers and where they kind of came from. You're not going to really see a whole lot of application for complex numbers until you get into upper level physics, where we start using it for anything from electronics to electronic magnetic fields, and in engineering they use complex numbers all the time in circuitries and again electricity flow, so on and so forth. So a lot of this will come back later, but you need to have it in your tool belt to be able to use it when you need to. Okay, see you next time.